So this is part 2 of my series on radioisotope dating, and here we're going to talk about kinetics of radioisotope decay. You might have had a little bit about this in Gen Chem when you talked about kinetics. So some of this may be review, and hopefully you'll learn a little bit in addition. So the first thing you should know about radioactive decay is that all of it happens via first order kinetics. Now, if you think back to the relationship between chemical kinetics and reaction mechanisms, this makes sense. Because when you're talking about what order reaction a particular elementary step has, it's going to be dependent on how many things are involved. So if that particular elementary step of your reaction mechanism is, O2 crashing into CO2, well, then that has two things involved in the collision, and so you're going to have a second order kinetics equation. But when it comes to radioactive decay, there's not something crashing into something. There's some sorts of nuclear chemistry where that does happen when you're talking about fusion, etc., but that doesn't happen when we're talking about radioactive isotopes. Radioactive isotopes are just sitting there. It's one atom by itself, and then suddenly it falls apart. There's only one thing involved. It's going to be a first order kinetic equation. And that's great because there are nice things about first order kinetics that don't happen with zeroth order or second order kinetics. So if you go back to the integrated rate laws, and specifically the integrated rate law for a first order reaction, you will usually find it written one of two ways. You will either find it written this way, where you have the natural log of A sub t, which is the concentration of whatever thing A that you're measuring at a given time, whatever time that you're measuring it, minus the natural log of the concentration at time 0, so that's the starting concentration, right? Equals minus kt, where k is the rate constant. But the way that you're probably more used to seeing it is this way. This is exactly the same equation, except we've employed our happy little log rules, and so that we've combined the natural log terms into one big term, right? So it's the natural log of the ratio of the concentration at time t divided by the concentration at time 0, and that's minus kt. So we can actually take this equation and we can look at it one of three ways when we're talking about radioactive decay. The first is just the way you see it here, where we're talking about concentrations. Sometimes we're actually going to do it on an atom by atom basis. And so here we have the number of atoms at time t divided by the number of atoms at time 0. And that's really related to the concentration, right? Because the concentration is nothing more than the number of atoms in a given volume. And then the third way that we can think about it is to think of it as an irradiance. So how many radioactive particles are coming out of this thing at any given time? Okay, so you can measure it at a particular time, and then you can measure the radioactivity of that, 2 years later or whatever, and see how much that has changed. You're just sitting there with your Geiger counter or whatever. Now, I mentioned that it was great that we had first order reactions, and the reason that that's great is because it allows us to use half-life in a meaningful way. So the half-life is the amount of time it takes for half of whatever you started with to disappear. So if you look back at the kinetics chapter in your Gen Chem textbook and you look at half-lives for second order reactions and zeroth order reactions, you'll see that the half-life changes depending on the concentration. And for first order kinetics, it is great because the half-life is constant no matter what concentration you start at. So if you look at this graph here, right, at time 0 we have concentration of 0.2. If half of that disappears, we're going to have 0.1, and so you can look at where that happens. It's a little past 100. It's like 120 or 125. And then how long will it take for that 0.1 to drop to half of 0.1, which is 0.05, well, let's see, we started at what did we say, 120? And now we're going to go to 0.05, and it's at time 240. So that's another 120, right? And then how long would it take for it to drop from 0.05 to 0.025, which is half of 0.05? Okay, now we have to sort of guess, but look, if you look at it's probably about right here. It looks like it's about 360, so it's another 120. And then you can just guess that, the next half-life will be at 480. That's right here. And that looks like it's about a quarter of 0.05, et cetera, et cetera. So it's just a constant thing. And so the nice thing about having a constant half-life is that the half-life is related to the rate constant. If you remember back in the first order reaction slide, we had this K that we said was the rate constant. That K being related to the half-life, remember, we can't figure those Ks out except by experiments. And if we can just measure the half-life of something, then it's very easy for us to calculate the rate constant. And because these rate constants are really truly constant for various isotopes, we can just look them up. We don't even have to do an experiment to determine what our rate constant is for nuclear decay of a given isotope. So let's quick put that into practice. You might have done problems like this in Gen Chem or possibly even some sort of biology, where they tell you, okay, a fossil is found to have 29% of the expected concentration of carbon-14. Here's the rate constant for carbon-14. How old is the fossil? So now what we're going to do is we're going to use this equation that has the ratio. And basically that ratio is going to be, what's the number right now? It's 29% of whatever we started with. At time 0, it used to be 100%. That's before a whole bunch of it decayed away, right? And then equals minus K, so there's our rate constant that we're plugging in, and times the time. Now, let's solve for the time. How long of a time has this carbon-14 been decaying for? And so I'm just going to rearrange that equation. And now we have something we can just plug into our calculator. And we get that the carbon-14 has been decaying for about 10,200 years. From a geologic standpoint, 10,200 years is very, very short. And it would be really nice if we could do this on a longer time scale. Let's look at something else we could use. Here's potassium-40, which, by the way, is an important tracer isotope in the ocean. And once again, I'm going to put it in terms of what percent of the original amount you have, okay? The difference between this and the last problem is we aren't given the rate constant, we're given the half-life. And usually that's the way it's going to be, because you can go look at the half-life on the chart of the nuclides. And so what we have to do is we have to use our half-life equation to calculate the rate constant. So this is the way that I showed you before. You can rearrange that and write the rate constant in terms of the half-life. Now let's plug in our numbers. The rate constant is going to be the natural log of 2 divided by 1.25 times 10 to the 9th years. And that gives us a rate constant of 5.545 times 10 to the minus 10th inverse years. So the units on your rate constant are always going to be the inverse of whatever unit you have on your half-life. Okay, now that we have our rate constant, let's plug that into our original equation. Again, using 18.45% divided by 100%, and then equals minus K value times T, and that gives us a value of T equals basically about 3 billion years. So that's all well and good, but the problem is if I give someone a problem like this, or that says if a rock is 13.7% of the original amount, like the first question out of your mouth when you see a problem like this should be, wait, how do we know what the original amount of potassium-40 in the rock was? And that is what we need to understand in order to actually do isotope dating, whether we're talking about decaying biological organisms or rocks down at the bottom of the ocean, because that's how we know how old the seafloor is, right? We need to know, how do we know what the original amount of potassium-40 was? So what we're going to do is we're going to look at how much daughter isotope we have and how much of the parent isotope we have. So let's just start by asking, how many atoms of a daughter isotope do we expect to see at any given moment in time? And we're going to develop an equation for this. So if you just consider the number of atoms of parent isotope that you start with, and let's just call that N0, so it's a number at time 0, and then you think about how many atoms are currently left, and let's just call that N sub t, so the number at our current time t, how many atoms of that daughter isotope will you have? And I'm going to start by saying the number of daughter atoms, and that's the D star. The star means it comes from radiogenic processes. D star is going to be N0 minus NT. In other words, the number of atoms of a daughter isotope is going to be the number of atoms of the parent isotope that you started with minus the number that currently exists. So let's think about why that's true. If you started with 100 atoms and now you have 20 atoms, what does that mean? 80 atoms of your parent isotope decayed away, and that's why you only have 20 left. What did they decay to? Well, they decayed to become a daughter product. So however many atoms of your parent isotope decayed away in the first place, that's how many atoms of your daughter isotope that you have right now. Okay, so that's where that equation comes from. It's just sort of a thought process of what's going on in this rock or whatever you're looking at. So now we're going to take our first order integrated rate law, and we're just basically going to work some exponential magic on it, basically raise each side to e to that side, okay? And basically at the end of that transformation, you end up with this equation here. N sub t equals n sub 0 times e to the minus kt. Well, what good is that? Let's go back and look at the two equations we've just talked about on the last two slides. We have the equation that tells us the number of daughter atoms, and we have a relationship between n sub t and n sub 0. So now what we can do is we can take this equation right here and plug it in for n sub t. And so now what we have here is we have an equation that relates the number of atoms of our daughter product to the number of atoms of parent isotope that we started with, given how much time has elapsed. This is something that we can calculate. So what we're going to be talking about is we're going to be talking about two different ways that we can use a radiogenic dating. One we're going to use to talk about geology, and that's for rocks, as I mentioned before. And the other one is to look at biology. And we treat these differently. In geologic radioisotope dating, we're going to look at concentrations. What's the concentration of the daughter isotope? What's the concentration of the parent isotope? And we can compare those. If you get to formally living things, so we're talking about biology here. Here we've got some really rotten tree trunks, okay? We can compare the current concentration of the parent isotope to the concentration we think it started with. Okay, you'll notice there's no mentions of the daughter isotopes in here. That's because the daughter isotopes tend to leave, okay? Because we're always looking at biological things that are dead, and therefore they are decaying, and a lot of that stuff escapes. So we're only looking at concentrations of the parent isotope. So these are two different things. And what do we need for that? First of all, we need to know the half-life of the parent isotope. And we also need to use a stable isotope for comparison before we measure either of these things, whether we're talking about just measuring the parent isotope or we're talking about measuring the parent isotope and the daughter isotope. We're always going to compare it to a stable isotope. Just like we did with stable isotope analysis, where we are always comparing the isotope we were measuring for fractionation with a more common isotope of that element, we are going to do the same thing here. So we always need that stable isotope, something where we can look at it and say, hey, we know the concentration of this thing and it's not changing. Those are very basic principles of radioactive decay kinetics. In our next video, we're actually going to put those principles into action.